Hello everyone, welcome to the OneClass channel. My name is Millan and I'm a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked mathematics questions at both the high school and college or university levels. If you're interested in getting some help with your homework or if you're interested in getting some tutoring, check out the links in the description below. Cool, so we can start this mathematic journey. When I switch my screen real fast, and let's pull up the first question of the day today. Cool, so this is the first question that we got on the menu today. So the question is asking us, what in the world is log base 2, that's important what the base is, 32 equals, well, let's figure this out. Now let's talk about what this really means. What this means is we're looking for 2 to the power of something. That's our result right here. We might as well just say that's x because typically when we have unknowns, we write them as x. It's a little bit easier to deal with. But what this really means is 2 to the power of something is going to be equal to 32. And we have to find out what that is. Okay, and once we have that, we'll know our answer. Well, let's think about how many times can we multiply 2 together to get to 32. Okay, that's how we're gonna find the power. Okay, so we know that 2 times 2, this is 4, times 2, this is 8, times 2, right here, this will give us 16, times 2, and that right there will give us 32, right? Because 16 times 2 is 32. So in total here, as you can see, we have 5 2's that are multiplied together. So this is equal to 32, which is equal to 2 to the power of 5. And that's pretty much what we're looking for right here. So as we can see, 2 to the power of 5 is going to correspond to 32, which is what we have here. So another way that we could write this is log base 2 of 32 is equal to a quick and easy 5. Okay, so just keep this in mind when you got logarithms. It just means, like, given the base to the power of something is going to be what's inside the logarithm here. Okay, so that's how you should proceed. And you know, if you know that, like, we know that 32 is going to be is a perfect is going to correspond properly to the logarithm of 2, and then we just do some multiplication by hand to figure it out. Otherwise, you can put this in your calculator. If we had like a number like 33 that's not so beautiful, it's probably going to be a lot easier to put that in your calculator, but otherwise this is the procedure to follow. Cool. So yeah, exactly, so this is good. Cool. Okay, so this is the next question that we got today, and the question is asking us, which of the following expressions is equivalent to 16? Now, what this, based on what we were given so far, and there's going to be multiple here because we have 5 options and more than one of them is going to be right, but since we don't really know what the base is, and if we assume base 10, like, none of these are going to be actually the number 16, so we're pretty much, I think it's just a formatting error here. So what it's really asking is, whoa, why'd you scroll? Who is equal to log of 16? 16 being the argument, which is like the thing that you pass into the thing. Okay, let me just make my webcam smaller here. Cool. Okay, so who of the following is equal to log 16? Okay, now let's take a look at our first option. Our first option is log 16 plus log 0. And the unfortunate reality here for this option is this is not a number. Is not a number. Keep that in mind. If you try to put log 0 in your calculator is going to be like, yeah, that's an error, buddy. It's not going to work out. And we can't add errors to numbers. So because this is not a number, this expression is not valid. Sean is invalid as a result. That surely is unfortunate, but you know, this is what a log graph looks like this. And as you can see here, there is a horizontal asymptote. I mean, not horizontal, vertical. Geez, sometimes this young mind of mine is makes mistakes like that. Vertical asymptote at x equals 0, meaning that no log 0 value. Okay, so if you this is why. You know, if you actually look at the log graph, this will be why. Okay, so the first option 1 disqualified. Our second option, option 2, it looks like this. So we have log of 8 plus log 2. Okay, now let me mention something ASAP fast, and I'll write this in green. So we have a log law that we can use. Log law, that's a fun thing to say, but we know this is the log law that I want to use, is log base of anything. Let's call that m, plus log base anything, but it's the same base, so a base, same for both. Let's call this n. This is equal to log base b of m times n. Okay, so if we have two logs that with the same base added together, you can take what's inside the log and multiply them together, and that's perfectly valid and perfectly equivalent. Okay, so let's go back to the black pen here. Okay, so given this principle, applying this to this situation right here, we can see that log 8 plus log 2 is going to be equal to log 8 times 2, which is, well, for those of you who are quick with the math, we can see that that is log 16. So this is nice. We found our answer here, so we know that option 2 is good. Happy face. Cool. But they said that there could be multiple things in here that correspond to this, so we got to keep searching through all of the other options to see what's going on. Okay, so our next option here is 4.log 2. So I'm pretty sure what this means is for option 3. Pretty sure what this means is 4 as a coefficient 4 times log 2. Okay, is this equal to log of 16? Let's find out. So another log law that is of interest, let's write that out in green, is that, so another log law is that when we have a number, let's call that a, multiplied by log of something, let's call that n. Another way that we can write this is log n to the power of the coefficient. Okay, so what's inside to the power of the coefficient in front of it, you can move that coefficient into the power, and these are perfectly equal, perfectly equivalent. Okay, so applying these principle to this situation that we have right here, so these two are going to come together. So 4 times log base 10, I guess, of 2 is equal to log of 2 to the power of 4, which is, now log 2 to the power of 4 is just 2 times 2 times 2 times 2, so that's 2, so that's 2, 4, 8, 16, so this is going to be log 16. And we can draw a happy face here because this is good, so option 3 is good as well. Option 3, good. Happy face. Okay, cool. Now we can keep it moving to option 4, because we got to check through all of them with no exceptions. Okay, so we got option 4. Let's go back to the black pen. We have 2 as a coefficient of log 4. And since we know that, we're going to use the exact same log law that we just used in the question, or in the situation one above here. So this will be equal to log 4 to the power of 2. And that's pretty much log 4 times 4, and that's log 16. Hey, isn't that exactly what we're looking for? It sure is. So option 4 is good too. Option 4, good, happy face. Okay, now the last one that we got here that we got to take a look at is option 5. Okay, now option 5 looks like this. We got log 20 minus log 4. Now remember how previously we had a situation like this where we have, or one of our log laws was when we have 2 logs with the same base added together, we're going to multiply them. We have a similar log law with subtraction where we when we have logs that are subtracted with the same base, they will be divided by each other. Okay, so let's draw that out in green. So here, a brand new log law is log base b of m, let's say, minus log base b of n. This will always be equal log base b of m divided by n. So honestly, it is pretty much the same as the addition one. It's just when you have a negative, you multiply in the reciprocal. Okay, but you can kind of see that this is the same as, you can combine the other 2 log laws, the one with the exponents here and the coefficient. You can combine that with this, and you can see that when you combine these 2 log laws together, this one and this one, you can get this one. Okay, now that's a little bit of homework that I'll leave for you, but just know that that's where this division one comes from. Okay, so let's put these 2 together. So given that we have log of 20 minus log of 4, we get log of, well, 20 divided by 4. Now what's 20 divided by 4? 5. And I am absolutely certain of that. And, well, 5 is not the same as 16, so, hate to say it, but option 5 is not going to work out. So let's think back to who did work out. We had option 4 that worked out, option 3 that worked out, option 2 worked out, and option 1 and 5, well, tough luck, they didn't work out. Okay, so, yeah, I suppose that, yeah, so the above answer all except the last option. Last one is log 5 instead, whoops, of a log 16. Cool. Okay, so this is the next question that we got on the menu today. It's asking us, write the logarithmic expression of a single logarithm with a coefficient of 1 and simplify it as much as possible. And what we're given here is 8 log 3x minus 2 log 3x minus 7 log 3y. Okay, cool. So we want to simplify this, which should not be too difficult, okay? So it says that we need a coefficient of 1. So the first thing that I think would be a reasonable thing to do is that we convert all of their coefficients to 1. Coefficients to 1. Okay, so how we can do that is, let's say we have a times log of m. We could rewrite this as log m to the power of a. Okay, so we can move those coefficients into the powers of the argument, and this will help us eliminate all the things in here. Okay? Oh, I think, oh, whoops. There are a couple different ways that we can interpret this. I think the given answer here, interpret it as the base, but we can interpret these as having a coefficient 2. And also that's z instead of x. Whoops, my bad. Okay, if this is the case, it is nothing to worry about. We can keep it as is. Cool. So let's just go with our assumption that we've written here. Of course, it would be perfectly valid if everything was base 3 and we just wouldn't have these 3 coefficients. But let's keep it like this, and we'll learn a little bit more, because we'll see what happens to those coefficients when we apply these log laws. Okay. So for the first one, we know that for the first term, we want to bring the 8 as the power of here. That's going to be log. Now remember, it's everything inside between the brackets of the log. So it's going to be 3x to the power of 8. The 8 came from there. Okay, now we want to convert this to a plus. Why do we want to convert this to a plus? It will make things a lot easier. Otherwise, we're going to have multiple divisions. But I mean, I guess the difficulty is about the same. But my preference is to convert everything to positive, so that we just multiply it together. So in here we have 3z, and this is to the power of negative 2. Remember, I brought the negative there with it. Okay, and the last term we are bringing the 7 over, so we do plus log. Now we have 3y to the power of negative 7. Okay, now I brought the negative over here as well. So I'll just write here, convert to positive by bringing negative into the exponent. Okay, so let's simplify this a little bit. So here, the x is going to remain like x to the power of 8. But the 3, we do 3 to the power of 8. So that is 30, that is 65, 61, x to the 8 plus log. Now, we can convert everything into a positive exponent if we just do, here we'll have 9z squared. So pretty much you did it just as you would normally, as if it was positive 2, but you send it downstairs on the fraction just because it's negative, okay? And then plus log. Now we'll have 1 over y to the 7, but it's got a coefficient on the downstairs of 3 to the power of 7. So 3 to the power of 7, 2187. Okay, cool. So this is our next intermediate step. Now, the next thing that we want to do is that we know that if we have log with the same base of m plus log of the same base with n, this is equal to log of the base of m times n. Okay, so if we have them added together, pretty much we can multiply all of their in bracket stuff together and make it a single log. And the coefficient is already 1 because that was our first step. So that brings us one step closer to victory. Here we got log. Now we just got to multiply all of the in bracket stuff together. So here on the upstairs we have, or we can show this more explicitly. So 6, 5, 6, 1, x to the 8. Multiplied by 1 over 9z squared, multiplied by 1 over 2187 y to the 7. Okay, and that's all in bracket. So we can do some simplification. So let's do the real numbers that we have so far. So we do 65, 61 divided by 9 divided by 2187. And this gives us 1/3 multiplied by x to the 8 over z squared y to the power 7. Okay, so I suppose we could write it like this. And we don't really need the 1 up here, so this will be our final answer. Okay, so let's circle this off. Final answer, assuming that the original 3's were coefficients. Okay, here in the given answer that we have, it was assumed that the 3 was a base. Honestly, you can't really tell like this, like you want to format it more properly to be more precise, but now we have a way of solving it either way. So this would be using 3 as a base, and this would be using 3 as an exponent. Okay, cool. So, above solution is good. Oh my goodness. Assuming 3 are bases, covered, use 3 as a coefficient. Okay, cool. Okay, so here we have the next question on the menu today, and the question is asking us linear versus exponential functions. Okay, so for linear functions, these are characterized by a always constant growth rate. Constant. Maybe instead of saying growth rate, because it could be shrinking, it could be an always constant shrink rate, always constant rate of change. For an exponential, these are always changing. Rate of change. For a linear, this is always going to be a straight line graphically, and this is always curvy, always a single curve in graphically. Single curve graphically. Okay, so let's see some examples of these in action. Okay, so let's do some linear examples. Your equation general form is going to look like this. Y equals mx plus b. Y is just your y value. M is going to be the slope. B is going to be your y-intercept. Okay, so if your equation looks like this form, it's linear. You should never have any powers on x. Never any powers on x, and you'll be linear. So they are a straight line. So maybe some graphical examples of this. Okay, if I'm drawing a XY area like this, this would be linear. Oh, let's do a lot of different colors so it's a little bit more clear. Let's put them in green, like grass. Here would be a linear. Just like here would be a linear. Here would be a linear. And here would be a linear. Straight lines equal linear. Okay, that should be the key characteristic that you're looking for when you're doing this type of analysis. If you see a straight line, you're linear. That's it. Okay, it really is that straightforward. Now let's see some exponential examples. Exponential examples. So they're always going to have this form. We're going to have y is equal to the base to the power of x. This is the general form. And you should see that the y value eventually is going to get really large really quickly, or you'll see greater rates of change at a certain side of the thing. It depends on your on the signs. All right, so if you see this form, base could be anything. It could be like any number, any real number. No imaginary numbers on exponential functions. If you don't know what that is, don't even worry about it. But real numbers only. Okay, so graphically, they look a little something like this. Now, there is not that much variation on what these might look like. So, an example of one, maybe let's do it in red, like strawberries. You might have them looking like this. You might have them looking like this. And in the other direction, I'll do it in purple. You could reflect it this way as well. Or this way. Okay, so what are some key characteristics that we can kind of see from here? Is that there's always one flat side and one curving up side. Flat side and one curving up/down, because it could be curving down, side. Okay, now the flat side will approach a horizontal asymptote. Flat side approaches horizontal asymptote. Okay, so these are the key visual characteristics that you should be looking for when you're dealing with exponential functions. You should see one curving up or curving down side and one flat side of the graph. And if you see that, it is most likely going to be a exponential function, and you definitely want to see the horizontal asymptote. That's where the flat side is going to approach, but the flat side is never going to get to that horizontal asymptote. It's just going to approach there. Okay, it's never going to quite get there. It's going to get very close, but never quite there. Okay, now some real life examples of linear and exponential functions in some real life situations is, well, maybe a linear function is that we are given a weekly allowance of $5 per day. So every day we're getting 5. So an example of this is like our total money is a linear function if this is the case. So every day it's 5. So we would follow this form. Y would be our total bank account. X would be the number of days passed. M would be 5 because we're increasing by 5 each time. And B, that's our y-intercept. In this case, is how much money you would start off with. Okay, so a graph of this function will look something like this. This would be your B value, X, Y, and the slope of rise over run is equal to M. So that's the slope. And in this case, with that allowance example, it'd be 5. Okay, so this is a fairly straightforward example of how we can see this in action. An exponential function in action could be something like compound interest. Okay, so every day that passes, I'm getting an interest amount, or my money is multiplied by, well, if you're really lucky, it could be something like 5%. So you get a 5% increase on your total money every time that you have a passing day, if you're for those type of things. So in that type of case, like every day you're going to have a multiplier between your previous number. So that is going to follow an exponential curve, because here to get to there you are times base, and times here we multiply by base. So the larger the number that you're currently at, when you multiply by base, you're going to increase faster. That's why you see like an accelerating growth rate. Okay, so this is, I would say, is a fairly complete rundown of exponential and linear functions. So the above solution is good. Cool. Okay, so here we have the next question that we have on the menu today, which is asking us, given the two inequalities, find and graph the solution set. Okay, so let's write this out on the writing surface. So we have the first inequality that we have is 2/3 of x has to be 2/3 of x minus 5/6 has to be less than 0. And our second one that we have is negative 3x has to be less than negative 2. Okay, so let's start with the first one, and we want to, our goal is to make an equality of x is less than or greater than or less than equal to or greater than equal to just some real number. Okay, we want to isolate x. So the first one, let's do the first one, which is 2/3 x minus 5/6 is less than or equal to 0. So we can treat these as if they are standard algebra situations. Minus 5/6 less than equal to 0. So for here, the first step that we can do is we can bring this to the other side by doing something like this. But we're going to add 5/6 to both sides, so that's going to 0 it on the left side, and it's just going to be a positive version of itself on the right side. Less than or equal to positive 5/6. Okay, I'm positive that's positive, and just like a math system, or just like all the math that we've done previously, like with regular equals and inequalities, so we're gonna do the reciprocal. Multiply both sides by 3/2 to neutralize it on the left side, and the right side will multiply it. So it'll be x less than or equal to 3/2 times 5/6, which is equal to 15/12. And, well, we'll divide the top by 3, divide the bottom by 3, and that gets 5/4. Right? Exactly, 5/4. Another way that we can write this is 1.25. So x has to be less than 1.25. That is one of our conditions of inequality. Okay, so that's the first one. Now let's go back up here and let's resolve the second one. Let's do this in a different color. Let's do this in green. Okay, so to do this, first we want to divide both sides by 3. So negative 3x is less than negative 2. So we're going to do multiply by reciprocal. But a star, a very important thing that some people do miss, and it is very dangerous if you miss this, is that when you divide by a negative number, you have to flip the sign or flip the direction of the inequality. Inequality direction must be flipped when dividing negatives. Okay, now let's think about the reason why. Okay, let's think about what would make this true. And keep in mind the inequality here saying that negative 3x is less than negative 2. That means what's on the left side here has to be deeper into the negatives than negative 2. So if x was equal to 5, we'd have negative 15 less than negative 2, and that's true because negative 15 is deeper into the negatives. So if we divide both sides by the negative, that's why we have to flip it, right? So to do that, we do x has to be bigger than 2/3. Okay, so that's why we flip the direction of this. And, well, I guess it really is this simple for this one. We just to isolate the x. So we know that x has to be bigger than 2/3, and 2/3 is equal to 0.66 to the infinite. Okay, so given these, let's do this in a brand new color, maybe blueberry blue. So we know that x has to be smaller than 1.25. 1.25 is bigger than or equal to x, and x has to be bigger than 2/3, which is 0.066 or 0.66. Has to be smaller than x. Okay, so given this, to do this graphically, well, let's say we have a number line here. Here's 0. Here is 0.5. 2, 3, 4. Here's 1.0. And here would be 1.25. Here would be 1.5. So about here, and 0.6, it's close to 0.67. So about here, x can occupy anywhere within this space. Okay, if this is a number line, so 0.67. Yeah, okay, so x can occupy anywhere in here, so this would be 2/3. This would be 5/4. This is the region that x can occupy. This would be like a graphical representation of here. X can be anywhere in here, and you know, we would have a agreeable. These inequalities would be okay with that. Okay, so this would be the graphic representation, and yeah, cool. So the above solution is good. Should have a visual representation. A visual representation. Yeah. Cool. That was fun. Okay, so here is the next question that we got in the menu today. Pretty exciting stuff. So we are given D equals A minus B minus C. Okay, so let's write that out in my black pen. D is equal to A minus B minus C. Now we can say plus A, just to specify and to be super clear that the A here is positive in this one. Okay, so given this, we want to rewrite the equation to solve for C, or pretty much isolate C on the left-hand side. When we find the equation, it's asking us what are the signs going to be. Okay, so let's go play by play to see how we can possibly do this. So imagine this, okay? If we add C to both sides, what would we get? We would get something like this, right? D plus C is equal to plus A minus B minus C plus C. Now you see here, they neutralize to 0. Okay, so yeah, that's fairly straightforward. So instead of, you know, that minus C plus C is effectively doing nothing, we could really just say, yeah, see you later, alligator, no need. Okay, so now we have D plus C equals A minus B. Now we want to send the D to the right-hand side, right? So we can subtract D from both sides. And we'll get a little something like this. We'll get D plus C minus D equals plus A minus B. Now the minus C plus C, we don't need to write that anymore because they neutralize each other. They're, we could write them, but it's not really helpful. It's like writing plus 0. Not very helpful. Minus D. Okay, so as you can see here, the D here and the minus D, so this is pretty much plus D minus D, they will 0 each other out, and we can just cross them out like this. So we can rewrite this as C equals A, positive A, minus B minus D. And this will be our final answer. Final answer, smiley face. Okay, so the signs that correspond to here is B is going to be negative. We have to do minus B. Well, we didn't even switch spots of B, so that, is fairly obvious. But D is going to have a negative in front of it. We have to be subtracting D because, we brought it over from the other side. Okay, so hopefully this algebra is nice and clear as to how we got through this process. And exactly. So it seems that we got the exact same thing here. So both of them are going to be minus in this case. So, okay, sounds good. The above solution is good. Ain't that a beautiful thing? Okay, cool. So this is the next question that we got on the menu today. So it's saying express the equations, or I guess the following two equations, in exponential form. Okay, so let's talk about what the first one that we got and what this really means with these logarithms and stuff. Okay, so the first one that we got, part A, we got log base 3 is equal to 81. I mean, log base 3 of 81. 81 is what we're passing to this function. You may call it that, the argument that you're passing to it. This is equal to 4. This is absolutely right, but what this really means is log means base to the power of something is going to be equal to the argument. Okay, so the log base of argument is equal to this. Okay, so this is just like to see where they come from. Now, how do we know that this is right? Okay, so pretty much what this is saying is that 3, which is the base 3, which comes from there, or this is the result is equal to 81, which is the argument. Argument. And we know this is absolutely right because 3 times 3 is 9. 9 times 3, 27. 27 times 3 is 81. Seems pretty reasonable to me that this is all right. Okay, so this would be pretty much how we could rewrite this in exponential form, and it's just to help us kind of conceptualize and understand the power of logarithms, why they're useful, and all that fun stuff. Okay, so just keep this in mind as what logarithms really mean. It means the base to the power of the result is equal to the argument that you're passing here. Okay, so that's part 1, or part A. Now for part B, we get a little something different. So that means that we have log. What's the base? Log is base 8. What's inside as the argument is 4. And the result of this is 2/3. Okay, this is a very, very interesting one. Pretty much what this is saying, following our previous rule, is that we know that the base is 8. Argument is 4. And this is the result. So this means that the base 8 to the power of 2/3 is equal to 4. Now, is this right? Now, exponents that are fractions are kind of tough to deal with, can't lie. But another way that we could write this is 8 to the power of 1/3 squared is equal to 4. And we know that because a to the power of b to the power of c is equal to a to the power of bc. So you know, if you have multiple things multiplying together, this works with fractions too. Like you can just like kind of separate them by you know, sending them outside of the exponent, kind of like putting brackets around it. Okay, and another way that we can write 8 to the power of 1/3 is the cube root of 8 squared is equal to 4. Okay, that's an equal way. If you have an exponent that's a fraction, you can make it the root instead. That's perfectly valid. Now, what's the cube root of 8? Something multiplied by itself 3 times is going to be 8. That's what we're looking for the inside of the bracket. So we know that 2 times 2 times 2 is 4 times 2. That's 8. So that we know that we got to have a 2 in the brackets here. So we have 2. And does this work out? 2 squared equal 4? You're absolutely right. We do have 2 squared equals 4. Okay, so with this one, when you have logarithms and fractions, and just bring the fraction as the exponent when you convert it into like an exponential equivalent, and separate the denominator and the numerators using this exponential law that I have here. And using that, you can definitely solve it down and definitely see that this stuff definitely works out and everything's beautiful. Okay, so yeah. 8 to the power of 2/3 is equal to 4. Absolutely right. And here, the above solution is good. Good job. Above solution is good. Cool. Okay, so next question that we got on the menu today is asking us, which one of the following options, kind of a multiple choice situation here, is equivalent to the expression 18x plus 6 minus 6x. Okay, we have to find which of these four options is it equivalent to. Before we even look at the options, one thing that we can do is we can try to simplify this. So first thing that we want to do is combine like terms. Like terms is whoever has the same, in this case, who has one x attached to them. Egg, who has x attached to them. And we can see that the 18x and the negative 6x, don't forget that negative there, that negative is attached to that term, negative 6x. These two will come together in harmony to make 18 minus 6x plus 6. 18 minus 6, that's 12x plus 6. Okay? So these are all equal to each other. We're just doing a little bit of a simplification process. Now for the next thing is, hey, you see how 12 and 6 are both divisible by 6? We can factor them out. So here we can say factor out 6, and we will have 12 divided by 6, that's 2, so there's got to be a 2 attached to that x, and 6 divided by 6, that's 1, so that's just 1. And this seems to be as simple as we can get it. Now let's try to see who matches to here. Okay, A, well, that ain't going to work out. A is not going to be a possible solution. B, well, the insides look similar, but it's a -1. That definitely can't work. C, whoa, C is a perfect match. So we know that perfectly matches C. Matches C. A C. Ha, I'm very funny. So it perfectly matches C, so it definitely matches C, and just for good measure, when we look at D, well, D, if we multiply that out, is going to be 6x plus 6, and that is not what we want. So D is disqualified. I see C is the only C that is working out that I see, so it's got to be C. Sounds good? Cool. So the above solution is good. Good would be better. Slightly showing the steps. Okay, so this is the next question that we have on the menu today, and it's asking us, choose the correct order of operations to solve the equation. Okay, so the equation that we have is x over 2 plus 5 is equal to 9. Okay, how do we solve this? Solve. Okay, so pretty much we want to isolate x, solve x, which just means isolate x, and we want to have eventually work this down into something that's just like x equals a particular number, a real number. Okay, and that's what we want to do. So the first thing that we want to do is, like, we want to when we do simplifications like this, simplify in reverse bedmass. Okay, so by reverse bedmass, I mean you want to do subtractions, and adds. This should be your first priority. Your second priority is multiplication and division, and divide. Third should be exponentials. And fourth should be brackets. Okay, so following this reverse bedmass process for simplification, the opposite of evaluation is getting the answer, simplification is isolating the stuff. So to isolate the stuff, you're going to want to do the reverse bedmass. So the first one that we want to do is that we want to bring this to the other side by subtracting 5 from both sides. So we'll have a situation like this. X divided by 2 plus 5 minus 5 is equal to 9 minus 5. Now you see, when we have plus 5 and minus 5, that is going to be 0. So we can put this in a box and put that box in the trash because we don't need that anymore. Okay, so we really have x over 2 is equal to 9 minus 5, and I know 9 minus 5 is equal to 4. Okay, so after this, what we want to do is we want to bring the 2, multiply both sides by 2, and we will have a situation like this. So we'll have 2 times x over 2 is equal to 2 times 4. Now we know that 2 times x divided by 2, so we have 2, like x over 2 is half of x, and we have 2 of them, that's 1 full x, so you know that will neutralize the 2's here, and this will just give us x is equal to 8. 2 times 4 is 8, fairly straightforward. Okay, so that's how we did it. When we simplified this whole thing, we got x equals 8. And what was the order of steps that we had to operate through? So the first thing that we did was subtract 5 from both sides. So the first thing that we did was step 4. And then afterwards, well, we multiplied both sides by 2. So that's 1. Step 4, step 1. Okay, and that was our process. So which one of our multiple choices corresponds to step 4 than step 1? Well, it's got to be B. So this is option B. And that would be a question complete. It's a fairly straightforward multiple choice situation, and that would be how we solve it. And yeah, so it's got to be B. And x is equal to 8 once you finally solve this whole thing. Okay, so here the above solution is good. Ain't that a beautiful thing? I think it is. Let me just turn the light on. Cool, so this is the next question that we have on the menu today. It is asking us to factor 64 x cubed, x to the power of 6, minus y to the power of 6. Okay, so to factor this completely, the first thing that might be nice to do is that we want to convert this 64 into something that's a little bit, actually no, that's not mandatory. You notice how we have like these two terms are both perfect squares. squares, and they are, there's a minus between them. So this is like a difference of squares or a conjugate situation. So conjugates. Conjugates is like a plus b, a minus b is equal to a squared minus b squared. But in this case, like our a's and b's are going to have powers on them, nothing to worry about. Okay, so if we were to apply this conjugate principle to what we have right here, we'd have, 64 is equal to 8 squared, right? So another way that we can write 64x to the 6 is we could write this as 8x to the 3 squared, right? And another way that we can write y cubed, y to the 6 is y to the power of 3, but squared. Okay, so using this, we can apply the conjugate principle as follows. So here we'll have 8x cubed plus y cubed. And here we'll have 8x cubed minus y cubed. Okay, so these are equal. Okay, so the next thing that is going to be convenient for our use is going to be the difference of cubes. Okay, so this is what the difference of cubes look like. I'll do it in a different color so we don't get any confusion here. Of cubes. Difference of cubes looks something like this. Okay, so here we have like a cubed plus minus b cubed. Unlike the difference of squares and the conjugates, there doesn't have to be a negative between them. It can be either positive or negative between them. Okay, so a like that, a squared plus or minus b squared is going to be a plus or minus b multiplied by a squared minus plus ab plus b squared. Okay, minus plus means that like these have same, and these have opposite. Okay, so given this, we can quite easily proceed with this. Okay, so the first one we have plus, so I'll underline that in purple, and then I'll write it out in purple just so we can kind of see who corresponds to who. So in this case, our a cubed is going to be a cubed is equal to 8x3. So that means our regular a has to be 2x, right? Because you can see how if we just cube a, we can get a cubed, and it will all work out. So in this case, we'll have, since they're added together, 2x, whoops, not a, 2x plus y, and then we'll have a squared, so that will be 4x squared, minus plus ab, so since we had plus in the first place, we have to do negative here. And a is 2x, b is y, so 2xy plus b squared, and that's just y squared. Okay, now for our second term, let's highlight that in something like a blue. So blue, since we have a minus between them, we're going to do a minus for it's going to be pretty much the exact same thing as the left, except the signs are going to be reversed. So 2x minus y then 4x squared plus 2xy plus y squared. Okay, and well, that's really as far as we can factor it. Okay, so you could see that to factor these any further, it's definitely not going to be easy. Maybe not even possible, given that like we can't really, since we have two variables in here, it's going to be a lot more difficult. So we could leave this as is right here, and this can be our fully factored solution. Fully factored solution. Okay, so we did difference of cubes with the conjugates and difference of squares, and or difference of squares with the conjugates and difference of cubes with the this equation right here. So you know, stay ready with that, and it will be very useful when you want to factor things out. So that's pretty much what we got right here in the solution. So the above solution, however, some issues with the negative not showing up. Cool. Okay, so the next question that we got on the menu today is asking us to multiply the following and write our answer in form. Okay, I'm gonna guess that means just like, you know, get the answer to the following. Okay, so the first one that we got on the menu today is minus 4 minus 2i, and that's in brackets. And the second term that we're multiplying in is 3 plus 2i. Okay, well, as we know, we can multiply the first two together. Let's do that in orange. So we'll have negative 4 times 3. Okay, and that may be in pink. We'll do the first of the first and the second of the second. So it'll be plus negative 4 times 2i. Okay, and then maybe in blueberry blue, we'll have this term multiplied this term plus negative 2i multiplied by 3. And then the last one, let's do it in green. We'll do this term and the last term. So this will be plus negative 2i positive 2i. I didn't really need to write the positive, but I did because I feel like it. Okay, so the colors were useful for where they came from, but now as we process this, we can, doesn't really matter where they came from originally. So let's just simplify this. We have negative 4 times 3, that's negative 12. Negative 4 times 2i, so that's negative 8i. Negative 2i plus times 3, so that's negative 6i. And then negative 2i times positive 2i, that will be negative 4i squared. So let's collect all like terms. So here we'll have negative 12 minus 14i minus 4i squared. And to simplify this even farther, all we need to keep in mind is that I squared is equal to negative 1, or I is equal to the square root of negative 1. If you're not too familiar about complex numbers, I'll tell you this. Anytime that someone has told you that you can't take the square root of a negative number has actually been lying. You can't, or we invented new math to help deal with that because it is very useful across many different fields, especially like for me, I'm an engineer. So in like a lot of electrical applications, there's a lot of, you know, this number used. But if you're not too familiar with it, don't worry about it too much right now. Just keep this relationship in mind, and everything will be groovy. Okay, so here we have an I squared term. So let's substitute that out for a minus 4 times minus 1. So to rewrite this will be negative 12 minus 14i minus, that's actually going to be a plus now, because see, the two negatives neutralize each other into a positive, so plus 4. So we could rewrite this as, well, negative 12 plus 4, that's negative 8, minus 14i. And that will be our answer for the part A. Part A. Okay, does that correspond to what we have here? Yes, but with formatting issues. Okay, no worries. Everything looks good. So we can move on to part B, which is very similar. It's definitely got the same type of energy. It's a similar looking question too. So here we have positive 2 minus 3i. Multiply that term with negative 5 plus, oh well, just I on its own. Okay, so following the same procedure, just to be a little bit more quick, I'll skip the color coding. So 2 times negative 5 plus negative 3i, oops, my bad, messed up the order, plus 2 times I plus negative 3i times negative 5 plus negative 3i times I, Captain. Cool, so let's simplify this. 2 times negative 5, that's negative 10, plus 2i, that's nice and easy, plus 15i. See the negatives, they neutralize each other here. Plus 3, or whoops, minus 3i squared. Now we know that I squared is equal to 1. I mean equal to negative 1. So we can rewrite this. After combining like terms, we have negative 10 plus 17i plus 3, because the negative 1 and the negative 3, they neutralize to positive 3. And this can be rewritten as negative 7 plus 17i. Okay, and that will be our part B. Definitely got the same type of energy as part A, but just with different numbers, but we can come to a similar result. And this is the form that we're expecting for complex numbers like this. So this is all good, all good. Okay, so the above solution is good. Formatting error on part A does not show the negative. Otherwise good. Okay, so our next question that we have on the menu today is, what is 240? 240 divided by 4. Okay, there are a couple of different ways that we can think about this. First, most easy way is just, ask our calculator, what's 240 divided by 4? And our calculator will tell us fairly quickly. But another way that we can kind of see this is more clearly is we can kind of see this, well, it might be better to kind of see this as a fraction, 240 over 4, but we know that 240 is last number is 0, right? So we know that it's easily divisible by 10, and we know that 24 times 10, 240, and that makes perfect sense to me. So 24 times 10, so that's 240 on the top divided by 4, and we only need to divide one of these two terms by 4 to make this work out. 10 divided by 4 is 2.5, not really a great number, but 24 divided by 4, we know that's going to be 6, right? So this is equal to 24 over 4 times 10. And 24 divided by 4, well, just thinking backwards, 4 times what is 24? It's got to be 6. So this is equal to 6 times 10. That's equal to 60. Right? Fairly straightforward. this is a good way to kind of think about numbers is what are they really made up of on the inside, right? So yeah, just splitting it up like this, we can make it nice and simple to calculate. But otherwise, like anytime you have doubts on a division situation, you want to ask your calculator, because in general, you're always going to have a calculator available. Anyone who tells you, oh, you're never going to have a calculator in the real world has never held a cell phone. So, you know, it is the way it is. Yeah, stay ready. So, yeah, answer is definitely 60. Many ways that you can think about this. Yeah, sounds good. So, the above solution is good. Oh, man. Let me just switch my screen real fast. Time flies when you're having fun, as the old saying goes. So those are all the questions that we have for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please subscribe and hit the notification bell below. If you would like to submit your own questions, we have video links in the description to help you accommodate that. And remember, if you like the video, please leave a like and a comment. And if you really like the video, share it with your friends. This has been Millan from OneClass. I hope to see you again soon. And don't forget, the mathematic magic is always a fun time. Take care, have an amazing day and an amazing night, no matter what time it is, and keep on mathing. OneClass, it's a good time. Mathematics, always a good time.